right, Firebase. My name is Erik Beeson. I used to, back in the day, I used to work at Sun Microsystems doing Java web application, servlet programming. And since then have been focusing mostly on kind of evolving into front-end web development. I started working with Firebase a couple of years ago now. I have no formal relationship with the company, but just a fan and do some consulting work and stuff related to Firebase. So just a quick show of hands, there's not too many of us. How experience with Firebase? Who's used Firebase in some capacity? Okay, about half. All right, and never used it at all? Okay, about the other half, so there we go. Okay, well, this should be good for everyone, I think. We'll see how it goes here. Whoops, I'm looking at the wrong window. Sorry, hang on. Okay, let's talk about Firebase. Great, so Firebase is a simple real-time synchronization of hierarchical data. It's generally thought of as like a database, like a storage system, and so I guess technically it is that too, but I tend to think of it as more of a sort of data synchronization service, because if you think of it like a data storage service, you'll expect it to do a lot of things that it doesn't do, at least not in the ways that you would expect. So like querying and indexes and stuff like that. And really storage, when you have real-time synchronization, storage is just kind of a special case of you have a node that is online all the time, syncing everything for you. So when I say it's simple, that's not just hyperbole, it really is quite basic. There is only one data structure, and that is an object. There are only 3 primitive data types. That's string, number, and Boolean. And while the data generally looks a lot like JSON data, it is lacking some stuff that we usually expect to see with JSON, such as null and arrays. Null in Firebase is sort of like undefined in the browser. Null is the absence of data. So there is not when you write null, you are removing data. And there is no notion of a location existing with no data there. That is the equivalent to the location not existing. So there is no null. There's no specific null object. There's just the absence of data. And there are no arrays. Everything is objects. There are relatively the operations available are relatively basic. There is set data and push data, which is a special case of setting, which we'll get to, and subscribe, and that's it. So the way we read data is to subscribe to changes in the data. And so this is, again, part of why I tend to not think of it so much as a data storage system, because you can't query for data. You can only start listening for data. The things to which we subscribe are fairly straightforward. The current value at some location. So this would mean that our node is, when this event fires, it means our node is up to date with everything that is at that location. And then there are a series of child events, child added, removed, changed, and moved. And these have to do with a special data. This has to do with ordering of data. And we'll see these things in use here pretty quick. And then there's also this one, hold on a second here, sorry. This shadow bothering me, there we go. There's also this one special metadata, singular metadata, right, called priority. And ostensibly, the purpose of priority has to do with ordering, but it actually does a lot more than just ordering, which we will see. So this is it. We write data. There's a couple of ways to write data, and we listen for new data. And value when we're fully synchronized, the child events for the incremental, as data is getting loaded, events, and that's it. So pretty simple in terms of what we can do. So lists are I said there are no arrays, but there are something that they call lists, which is like a data structure pattern. It's using objects in a way that makes them operate very much like arrays, but with some benefits. So when we have an array, it maybe looks like this. And with an array, the names of these items in the lists are just the indices in the array. And the position of the items in the list depends on is the same as its name. It depends on its name. So, item 0 is first in the list because it is item 0. Lists, on the other hand, look like this, similar, except now it's not an array, it's an object, and it now has these unique identifiers. And so instead of using these indices, 0, 1, 2, 3, we now have these unique IDs to identify the items in the list. And now the position of the list depends on this priority metadata. There is, if you've worked with Firebase at all, you know that there are arrays. You can write arrays, and you'll get them back, and what you'll get back as arrays. But I would caution against it, because you find that once you go very far down the road of dealing with your data, arrays become very unruly in a synchronized environment like this. Basically, the rule of thumb is that you would use arrays wherever you could transparently replace them with a serialized string. That is to say, wherever you would only ever want to set or get the contents of the array in one single operation, never where you would want to drill into that array. The way that arrays are implemented in the web client, at least, is that it's basically a feature of the client library. It doesn't really exist, and it is determined by the shape of the data. And so be careful about using objects that have numeric keys, because they'll look an awful lot like arrays, and you can get into some weirdness where the client thinks you will treat something as an array instead of an object for you. So that's lists. So let's see what it all looks like now, actually using it. So to write some data, and this is like for the JavaScript library, and so this is on the web or in a node environment. To write data, we just have some reference to this Firebase object. And like I said, it's hierarchical, so we, under user, we set some data, right? So far, so good. 2 keys, strings, straightforward. Okay. Reading data, we can bind the on value to the root of the entire Firebase instance. And this will load the entire contents of this Firebase instance into memory and keep it synchronized, keep this node synchronized. This is this kind of looks like a select star from your relational database, but this is actually not all that unheard of to do if you're, for example, you have workers or something where you want to keep You keep everything about all of the data in a Firebase instance cached on your local node. Kind of doing this will get you there. And then for lists, this is where those child events come in. Lists, we can subscribe to changes in the list. So when a node gets added, a child gets added to a list, and a child gets removed from the list, that triggers these events. The child events and the value event can kind of work together, because the value event fires, the child events fire as data is being downloaded, and the value event fires once all of the data has been downloaded. So querying, which is, like I said, not really quite querying. It's more like selecting what we're going to, choosing what we're going to subscribe to, selective subscription. The operations available for doing that are limit and start at and end at. Limit just limit just determines how many children we'll be looking at a time, and start at and end at are a way to filter based on priority. I said that priority metadata is, I think, kind of a misnomer to call it priority, because it is more than just ordering. It's about the only primitive that we have in order to be able to filter. So for basic querying. So this is adding an item to a list. So we have the to-dos, we add another item, and push is the operation that generates that unique ID that we saw in the list versus arrays comparison. And when we have pushed this, this new to-do item, we can also set a priority for it. So this has priority 1, and now when we want to go look for it, we can say we want all of the priorities that are between 1 and 1 inclusively, and let's only get 10 of them, and that creates this query object. And then to read from the query object is the exact same as from reading from any other Firebase reference. So we just subscribe to events, and the child added, of course, will get called as initial data is loaded, and then as data changes to meet this criteria, and removed as data is either deleted or, again, changes to no longer meet that criteria. So indexing, so the basic, there is no index like in Mongo or a traditional database, but we can leverage that priority metadata to sort of build an index with it. And so if we have our setting this user data again, this time instead of set, we set with priority and specify the priority to be the email address. And then we can query for that email, all of the users for which the priority is that email address. And this callback will then get fired just for this user. Now, this is not a unique index. There can be multiple users with, multiple users with the same email address listed here. So this is not an ideal way to maintain some kind of unique index, but this is the quickest way, the simplest way to be able to sort of query for some data based on some property. in order to maintain like a unique index, we have to use multiple locations, basically. We have we would have a separate section of our Firebase instance where we maintain indexes. And in that place, we can use the email address as a key to a location, and then use security rules to ensure that that location is only written to one time. So security rules are a JSON document that defines access control and data integrity. So schema validation and access control. Security rules end up, it's very powerful, but it ends up getting awfully unruly awfully fast. So here's a basic example of what some security rules look like. Yeah, let's not get into it. There's reads and writes and validates, those dot things, and then the top keys, rules, room name, messages, $ room ID, those are all referencing locations. And then all of that stuff in there, all those things and those strings, data exists and new data exists and new data has children. That's all, that validate one is doing some schema enforcement. So it says that you can't write unless there's got all these children. This is complicated and a hassle to deal with. But what you get from this is you can sort of define the portion of your application logic that is access control and schema enforcement in a file, which you then upload to your Firebase instance. And this is how you can have clients, your web client in JavaScript or your mobile client or whatever, communicating directly with your backend in a safe way. It's by having these security rules that dictate what the clients are and are not allowed to do. I don't want to spend time on this because I think it kind of sucks. What's actually going on in there is we have a schema and we have the access control. And those things are different. And the folks at Firebase recognize this. And there is a new thing now called Blaze Compiler, which takes a schema and takes an ACL definition and spits out those security rules. So this is kind of new stuff, but it's on GitHub, and you can play with it. I suggest you check it out. Instead of JSON, it uses YAML just for the more compact syntax. And access control looks like this. So now we say at the root, everybody can read. It's world readable. And auth is a global variable that is the current logged in user's authentication data, which is provided to the security rules processing when it runs. And so we say if the auth UID is not equal null, if the current user is logged in, that's what's going on there. So if someone is logged in, then they can write. So this is fairly basic, just as you must be logged in order to be able to write, and then you can write anywhere, and anybody can always read everywhere. Expressions like that come up a lot, and there get to be sort of more and more of them, and so you can refactor those things out into reusable functions. And these functions can take arguments, and so now the ACL portion of this, instead of this this mess back here, and these are, sorry, this is not the same, these are not the same sort of schemas here, but it's just, yikes. Now it looks like this. And for the schema, we can just specify a schema that looks a lot like JSON schema. So if you're familiar with JSON schema, this is pretty much that. So this would be the schema for like that user object that I showed back at the beginning. It is an object. It has two properties of type string, one called name, one called location, and these are the only properties that it may have. You can't add anything else to this object. So if I included a first name and a last name or whatever, the client would fail to write when it tried to write this if it had a schema like this. And there's all kinds of different types, and so there's enums. You can say you can only have particular values. You can say that there's it is a number and it has some number range. And if you've worked with schemas like this much, they tend to sort of get bigger and bigger. And so you can define models and then reference them in multiple places. And you can also provide examples and non-examples, and the Blaze compiler will, the security rules will ensure that the data coming in, that your schema, sorry, the Blaze compiler will ensure that your schema matches your examples. Here we go. So far these have all been quite trivial schemas. This is all sort of at the root. I mean, this basically means there can only be one. I mean, there could just be some number in the root of the location. That's clearly not actually very practical. More practical, though, is something that looks like this. And so this is the object that defines again, from the root of a Firebase instance, says that this object, we have users, and so this is again like that structure that I showed where I said, I guess I had to-dos before. Okay, so this is users, and the $user ID right there is a wildcard. So that's saying /users/something that goes there, and that something must have an ID whose, and now next is the value of the data being written, and previous is the value that was in this location before this write happened. So we have these next and previous variables that are globally available to our security rules that represent the data coming in and the data that is already there. So this says that the ID of this user object has to equal this same $user ID as is in the parent path, and that that we can only write to this once, for each user. So we cannot overwrite a user because we say, now this is under the user ID, that there can't be anything there in order for this to write to succeed, right? And so this ends up creating sort of a data structure that security rules that ensure that your data structure looks kind of like that. That under /user/Erik, you end up with an object whose ID is Erik. Let me show something real quick. The next constraint here.
You're basically saying that you can only write it, but it has to be the same as what it is, so why allow that at all?
Right, so what this is, so next is the incoming data at the current location, sort of in the object hierarchy, in the schema hierarchy. So next, right, that the next equals user ID line there. Next is the value of the ID
That's the ID value.
property, yeah, the ID value. So at that place in the schema, next is the ID value. And up, and so that's why then the line below that then is indented back one, because that's now referring to sort of that whole object.
Okay.
So it says that, the user ID, that /user/user ID, whatever that is, cannot already exist, but that the value of ID inside the object must be equal to whatever is in that path. And I'm just going to show one thing real quick, and then I'm done. I'm sorry that this session was advertised as being so long. I told them I didn't really have that long to go. But all right, here, what do I want to show? Oh, I can't see. Oh yeah, how about that? Yes, yes. So a more, I'm not going to go through this line by line, certainly, but just a kind of, to give you an example of what it looks like. All-in-one file now, the functions like we talked about, these schemas, and again, there's definitions section, so you can reuse parts, reuse parts of your schema. All over the place in here can be making reference to those Boolean functions that we defined up above. And then the actual schema itself, we have users, a user ID, and under each user ID there is an inbox and outbox. And so again, this is just that part is just the schema. Over here. Oh yes, that part is just the schema, and then the actual access control says that we can, anyone can write to anyone's inbox. Only the owner can delete from their own inbox, and et cetera. Anyways, so that's what it looks like. And then, let's see if I can actually get it on the screen. There we go. We compile it. We get back this rules file. And here is the output. Here is what we could have written to have done all of that. And this is, it's only 57 lines long of this kind of stuff. So, so this is the actual file that gets uploaded to Firebase. There we go. So that's pretty much what I got. I must disclaim again that I'm not, I don't work for Firebase, and so please don't judge them based on my performance here. But if you're looking for more resources on Firebase, there's a Google group that's really good. It's quite active, but quite good. All of or most of the devs are on there and quite responsive and friendly. The Firebase channel on Freenode, IRC channel on Freenode, where you can find me most of the time. Their developer docs are excellent. They have a new feature that came out on Friday because apparently they knew I was going to give a talk and tried to throw me a curveball, which I didn't get to making slides for. But they have a new beta query interface that allows you to basically, like I was showing what you could do with priorities, you can now do that with actual fields like list objects. So you have a list of things, and instead of with a to-do list using the priority to set the priority of the to-do, you can now have a field for priority, and you can query multiple fields and choose which field to query and stuff like that. So this sort of screwed up my story about it not really being a data storage service, because this makes it a lot more like a data storage service. But it's pretty cool stuff. It just adds a couple of extra functions. In fitting with how they generally do, it's pretty simple. but I think quite powerful. Looking forward to seeing what they come up with that there. And then that Blaze security compiler that I showed is on GitHub, and it works, and it's cool. And you should go check it out. And that's all I got. Any questions?
Yeah. Not a direct comparison, but what do you think of like the Meteor platform opposed to what it does compared to Firebase?
What do I think? The question was, what do I think of the Meteor platform compared to Firebase? I don't know. It seems I have my only experience with Meteor comes from more of a like sort of in relation to Angular or Knockout or something as a kind of a web framework with synchronization.
I actually don't know much about it either. I just went to a talk earlier this morning, and I was like, oh, I'm doing that with Firebase. I thought it was kind of interesting how they're.
Yeah, so Firebase is sort of just a closed source hosted service that their free plan is quite generous. If you want to go play with it, it doesn't cost anything to get going with. Meteor, of course, an open source, I guess kind of the web app framework and all that stuff. I think clearly, you look at parse or pubnub or there's the clearly sort of real-time synchronized messaging and data is the thing, and so I think there's a lot of different angles on that. But I personally, I like how quickly I can sort of I completely forget about loading and saving and all of that with data. It's kind of just building on Firebase. My development paradigm has shifted into just kind of everything is always synchronized all the time. The data is just sort of there, and I don't really think about it. And so I guess that's very much how Meteor is sold also, is that it's kind of just everything is where you need it, when you need it. You don't really have to think about how it got there and that sort of thing. Any other questions? Yes?
If I have a validation schema using Blaze, is there a way to reuse that schema at client side so I don't have to rewrite those validation rules? Say in Angular?
You mean the question was, can validation rules written for Blaze be used on the client? You mean like to inform a UI or something like that? So the syntax of the schema definition is very much like JSON schema. It is JSON schema. So anywhere that you could sort of, given a JSON schema, enforce, do some sort of schema enforcement, then yes. So not directly. Not that that's like a feature of Blaze compiler, but the syntax is the same. And so, I've worked with I have worked with a component called the JSON form, or another called JSON editor, that is given a JSON schema, generate the form and do the validation and all of that kind of stuff. It would work great with that sort of thing. So, all right. Any other questions? I'll be around. Welcome to. I'm happy to chat about it, and I'm a little less awkward in person, I think. So, thanks very much.